I want you to imagine the last time you drove down a highway and you passed one of those massive, dizzying grids of high-voltage power lines just cutting across the landscape.
Oh, yeah, those giant steel towers.
Right. Exactly. We drive right by them every single day, and we almost never think about the sheer human cost of maintaining that grid. I mean, we are talking about people literally dangling from helicopters or crews climbing these massive vertigo-inducing steel towers just to make sure, a single bolt isn't rusting out.
It's incredibly dangerous work.
It really is. But right now, there is this quiet revolution happening right above our heads.
Yeah, and it really is a profound shift. And I think the craziest part is it's happening largely out of sight for the average consumer, which, well, it makes it all the more fascinating to explore.
Absolutely.
We're basically replacing massive, heavy machinery and immense human risk with something much smaller but infinitely more sophisticated.
And that is exactly why today we are taking a deep dive into the mechanics of that revolution. Our goal for you today listening to this is to understand exactly why the biggest utility companies on the planet are suddenly just obsessed with drones. And spoiler alert here, we are going to learn why buying the actual physical drone is the absolute easiest and arguably the cheapest part of this entire equation.
Yeah. Setting the context here is crucial because, drones themselves aren't exactly new.
Right. I think everyone's seen someone flying one in a park.
Exactly. We've had them for years. But we have reached a very specific tipping point where the math has just become undeniable for these energy companies.
Okay, so it's a financial thing.
Yeah. What we are looking at right now isn't just a marginal incremental tech upgrade. It is a fundamental category shift in how we manage and interact with our critical infrastructure.
Welcome to the Red Raven UAS podcast.
We're here to help you navigate the pretty complex world of unmanned aerial systems. At Red Raven, we work with public safety, utilities, and enterprise teams. And our focus is really on one thing, helping you launch and grow a drone program that's safe, compliant, and actually ready for your mission. We do the consulting, the strategy, and the hands-on training that turns an idea into a real operational tool.
And you can find all their training philosophies and resources over at redravenuas.com.
The mission for today is to figure out why this isn't just some marginal tech upgrade. It is a total category shift in how we manage physical infrastructure.
A complete paradigm shift, yeah.
We're going to break down the mechanics of the tech, the regulatory hurdles, and what it actually takes to get one of these enterprise programs off the ground. If you're listening to this, you likely interact with the power grid 100 times a day without even a second thought. Most people do.
Right. But today, we are looking at how a specific category of technology, drones, is fundamentally revolutionizing the energy and utilities sector.
Because the stakes for that kind of infrastructure management, they've simply never been higher. We're dealing with an aging, highly volatile grid.
And the margin for error there is shrinking every single day.
It really is. Imagine standing just outside the chain link fence of a multi-million-dollar high-voltage utility substation.
Yeah, that air literally hums.
Right, it hums.
Yeah.
And for decades, the only way to inspect that maze of energized steel and copper was to actually send a human being walking right into the yard.
Which is terrifying, honestly.
It really is.
Yeah.
One wrong step, one dropped tool, and you are looking at a catastrophic, life-threatening arc flash. But today, a utility company can deploy a robot that spots a microscopic thermal failure on a transformer weeks before it actually blows.
And all without a single human ever having to open that gate.
Exactly.
So to understand the velocity of this shift, you really have to look at the baseline reality of the U.S. power grid.
Which is not great, right?
No, it's really not. The American Society of Civil Engineers, they gave the U.S. energy infrastructure a C- in their 2025 report card.
A C-? Wow.
Yeah. So utilities are staring down massive regulatory pressure to inspect their assets way more frequently.
And they need highly documented proof of condition, right?
Exactly. Traditionally, if you wanted to inspect a transmission line, you had to schedule a helicopter.
Which is a whole ordeal.
Oh, absolutely. That means aviation fuel, finding a specialized pilot, and flying a massive aircraft hundreds of feet in the air to take, quite frankly, mediocre photos.
Right. Or you send those specialized climbing crews up massive towers.
Yeah. And that often requires actually de-energizing the line, taking it totally out of service for days.
I understand the inefficiency of helicopters and climbers. For sure. It's like moving from a horse and buggy to a car. It changes the whole system. But if you're listening to this, you might be wondering, drones have been commercially viable for over a decade now.
Right.
If the grid is in such bad shape, why hasn't this industry completely turned over already? What took so long?
Well, what's fascinating here is that the physical hardware, the drone itself, is actually the easy part of the equation.
Really? The easy part?
Yeah. The reason this massive shift is happening right now is a sudden convergence of pressures. You have that aging infrastructure finally hitting a critical failure point.
Colliding with skyrocketing insurance premiums for utility companies.
Exactly. But the real barrier hasn't been the technology itself. It's the operational structure.
Okay.
Handing an engineer a drone is easy, but building a massive, legally compliant program with the right data workflows and regulatory frameworks.
To actually turn aerial photos into proactive maintenance decisions.
Right. That took years for the industry to actually figure out.
Let's talk about the math of that operational shift, because the difference in efficiency is just staggering. You take that same transmission line inspection we talked about. Instead of a helicopter and days of grid downtime, a two-person team just pulls their truck to the side of the access road.
And they launch an aircraft that hovers, maybe 15 feet from a live, fully energized wire?
Yeah, and nobody goes up in the air. The power stays on. It's the difference between taking a single blurry Polaroid of your house once a year,
right,
versus having a 247 MRI scan of your home's foundation that flags a crack the absolute millimeter of forms.
That MRI analogy is spot on, really, because of the sheer scale of what these programs have to cover. When you dig into the sources, there are 5 core, highly distinct operational environments.
Right, and you just mentioned transmission and distribution earlier, the high-volume corridor work.
Yeah, and to give you an idea of what that scale looks like, Georgia Power used UAS to inspect 1,400 miles of lines, and that was in 1,000 flight hours over 8 months.
So that's about 14 miles a day of continuous high-resolution data capture?
Exactly. It's a massive undertaking.
But power lines are just the connective tissue of the grid. If you follow those lines, you eventually hit the nodes, right? The substations. And from an operational standpoint, flying a drone over an open rural power line has to be a completely different discipline than navigating a dense electrified substation.
Oh, it requires a completely different methodology. Substations are high-value, high-consequence choke points.
Yeah, if a transformer goes down, an entire city block or a hospital loses power.
Exactly. So drones inspect these facilities primarily using thermal imaging, because physical components, they don't just snap instantly, they degrade.
And as a connection degrades, electrical resistance increases.
Right, and resistance generates heat. So a thermal camera can actually detect a 2-degree temperature differential on a ceramic insulator from 100 feet away.
Which is wild. That allows the utility to replace the part during a scheduled maintenance window.
Instead of responding to an emergency fire at 2 a.m.
Right, which brings up a fascinating contrast with the third operational environment, solar farms.
Ah, yes.
If a substation is a dense, three-dimensional maze, a utility-scale solar farm is just a flat, sprawling ocean of glass.
It really is.
I was thinking, inspecting a 500-acre solar installation from the ground has to be like trying to find a single dead pixel on a stadium-sized TV screen by walking right up to the glass and just squinting.
That is exactly what it's like. You are looking at thousands of panels and physical defects like microcracks or bypass cells. They're virtually invisible to the naked eye from the ground.
But from the air.
From the air, a drone doesn't just fly around randomly. It runs an automated, precise grid pattern, and using those same thermal sensors we talked about, a dead cell on a solar panel shows up vividly.
Because it isn't converting solar energy into electricity anymore, right?
Right, it's just absorbing it as raw heat. So the drone can map the entire installation in an afternoon and pinpoint the exact GPS coordinates of every failing panel.
That's incredible. And then you have the complete inverse of a flat solar farm.
That's a whole different beast.
This seems like an absolute nightmare for an aircraft. You have 300-foot spinning fiberglass blades, massive wind shear off the coast or the plains, complex aerodynamics.
Yeah, wind turbine inspection is one of the highest risk profiles in the industry. Historically, you'd have a technician in a climbing harness actually rappelling down a blade.
Which sounds terrifying.
And they'd be physically tapping the fiberglass to listen for delamination.
Wait, delamination?
Yeah, that's where the layers of the blade actually start separating.
Oh.
But now, a specialized drone performs an automated vertical spiral around the tower.
And using high-resolution optical zoom, it can identify microscopic lightning strike burns or leading-edge erosion.
All while the technician stays completely safely on the ground.
Amazing. So we've covered lines, substations, solar, and wind. The fifth environment the sources highlight is pipelines.
Right.
This is pure, brutal linear infrastructure. We are talking about hundreds of miles cutting through mountains, swamps, forests.
Yeah.
But the primary goal here isn't just checking the pipe itself, right?
No, it's really right-of-way management.
Right.
They are looking for vegetation encroachment, tree roots threatening the pipe, or unauthorized third-party excavation.
Oh, like a construction crew digging near a high-pressure gas line without checking the maps.
Exactly. A daily drone patrol can spot that backhoe and dispatch a team before a catastrophic strike occurs.
There is a massive invisible threat to the drones themselves, right?
Yes.
Specifically when inspecting transmission lines and substations, electromagnetic interference, or EMI.
It's a huge issue.
If you're listening, you might just assume you can take a high-end consumer drone, throw it up near a power line, and start recording. Why does EMI make that impossible?
Well, alternating current flowing through high-voltage lines generates massive magnetic fields. And standard drones, they rely heavily on GPS to hold their position in the air. But the signal coming from a GPS satellite 12,000 miles away is incredibly faint. So when a drone flies into the magnetic field of a 500 kilovolt transmission line, that EMI completely drowns out the GPS signal.
Oh, wow.
Yeah, the drone's internal compass gets totally scrambled. If you fly a standard consumer drone into that environment, it will likely lose its positioning, drift wildly.
And either crash into the live wires or drop out of the sky entirely.
Exactly.
Which is the absolute last thing you want happening over critical infrastructure.
Yeah.
So how do these enterprise platforms survive the EMI?
Well, if we connect this to the bigger picture, the payload dictates the platform. Utility programs utilize specialized aircraft equipped with visual odometry.
Visual odometry, what is that?
Instead of relying on satellites, they use an array of downward and forward-facing cameras that constantly map the ground and the structure in real time.
So the drone holds its position by visually locking onto the physical environment.
Exactly. These platforms are designed to carry specific, heavy payloads. You might need to carry a LiDAR sensor, which pulses millions of lasers a second to create millimeter-accurate 3D maps of vegetation clearance.
So you need an aircraft that can carry that heavy LiDAR sensor, fight through 20-mile-an-hour wind shear,
Yeah.
and ignore electromagnetic interference. Understanding the sheer variety of these environments, navigating EMI at a substation, mapping 500 acres of solar, fighting wind shear at a turbine. It forces a massive logistical question.
It really does.
If you are a utility executive listening to this, how on earth do you staff for this? I mean, the skill set to fly a pipeline is completely different from thermal mapping a substation.
Yeah.
So do you build an internal team or do you contract out? It's the classic build versus buy dilemma.
It is the most consequential structural decision a utility makes. Building an in-house program is generally the standard for high-frequency daily operations. The core advantage is institutional knowledge. I mean, an external contractor flies your substation once a year. They see a snapshot.
But an internal pilot flies that yard every month.
Exactly. They get to know your specific assets. They know what normal looks like for that one notoriously cranky transformer on the edge of town.
Right, so they know instantly when the thermal signature looks anomalous.
Spot on.
Sources specifically highlight Florida Power and Light as the gold standard for this internal model. They have a highly trained internal team that can deploy instantly.
Which is crucial in Florida.
Yeah. When a hurricane wipes out a grid, you can't just call a contractor and hope they have availability. You need your own people in the air the minute the storm clears.
Right.
But building that capability is a heavy lift. Sources estimate it costs between $30,000 and $60,000 just to establish a basic Phase 1 internal program.
It's an investment for sure.
So let me push back on this model for a second. In a modern gig economy, why wouldn't a utility just Uberize this? Why take on a $60,000 capital expense for hardware that will inevitably be obsolete in 24 months?
It's a highly debated point, and for low-frequency needs, like a once-a-year structural audit, contracting is absolutely the right call. It keeps overhead low.
Right.
But for daily operations, controlling your own data and leveraging that institutional knowledge massively outweighs the equipment depreciation.
Interesting.
Because the ROI mechanism for an internal program is incredibly fast. You immediately offset that capital cost through labor displacement. I mean, you aren't paying hourly rates for helicopter fuel and specialized flight crews.
That makes sense.
More importantly, the ROI is realized through outage prevention. If an internal pilot catches one failing component before it cascades and takes down a city's power grid—
They have avoided massive regulatory non-compliance fines.
Exactly. That single catch pays for the entire drone program 10 times over.
Okay, that makes perfect sense.
Yeah.
You're buying control and immediate response capability. So where is the industry settling on this?
The prevailing strategy is a hybrid model. Internal teams handle the daily routine inspections and immediate post-storm assessments where speed and familiarity are paramount. Then, utilities contract out the highly complex, specialized jobs. If you need a massive, county-wide LiDAR survey that requires a $500,000 sensor, or if you have a massive post-hurricane surge and need 50 extra pilots for exactly 1 week,
You bring in the contractors. Okay, so whether you build an internal team or you hire a fleet of contractors, you hit a massive, unavoidable bottleneck.
the regulations.
Yes, because it turns out the sky is incredibly regulated. You can't just throw an aircraft over a 100-mile pipeline, even if you own the pipeline and the land underneath it.
The regulatory framework is the ultimate governor of scale right now. The baseline operational rule in the United States is FAA Part 107, and it dictates that commercial drones must fly below 400 feet, avoid flying directly over unprotected people, and most critically—
The drone must remain within the pilot's visual line of sight at all times.
yes, VLOS.
Now, here's where it gets really interesting. Visual line of sight is a brutal limitation for utilities.
Crippling.
If you are listening to this and trying to imagine inspecting a 100-mile transmission corridor under Part 107, it's like buying a high-performance sports car, but being legally required to never shift out of first gear.
Perfect analogy.
You have an aircraft that can technically fly for 20 miles on a single battery, but legally your pilot has to stand in a field, fly the drone a few thousand feet until it's a speck in the sky,
Bring it back, land it, pack it into the truck.
drive a mile down the access road, and launch all over again.
It's absurd. Or utilities try to bypass that by setting up a daisy chain of pilots standing miles apart, handing off the radio telemetry signal like a baton in a relay race.
Oh my God.
It is an operational nightmare. It completely kneecaps the efficiency of linear infrastructure inspection.
Right.
But there is a monumental regulatory shift on the horizon. The FAA has published a Notice of Proposed Rulemaking, an NPRM, called Part 108.
Part 108.
And it specifically addresses BVLOS, Beyond Visual Line of Sight.
This is the unlock the entire industry is waiting for, right?
It changes everything. Currently, to fly beyond visual line of sight, a utility has to apply for a complex per-operation waiver, proving they have ground-based radar or visual observers to avoid other aircraft.
Which sounds tedious.
Oh, it is. But Part 108 will standardize the rules for the entire industry. When it is finalized, which is likely in 2026, a pilot sitting in a remote operations center in Chicago will be able to launch a drone from a docking station in rural Illinois,
Wow.
fly it 50 miles down a transmission corridor using cellular network telemetry, and land it at another dock, completely legally.
Okay, but if I'm a utility manager and Part 108 doesn't drop until 2026, why wouldn't I just wait to build my program until the rules are finalized? Why spend the money today?
Because building the operational muscle takes years. If you establish your internal safety protocols, your data pipelines, and your pilot proficiency today under the restricted rules of Part 107,
You are positioned to instantly scale the minute Part 108 goes live.
Exactly. The utilities that wait until 2026 to figure out their hardware and training, they will be years behind the curve, and their infrastructure will continue to degrade while they play catch-up.
Which brings us to what the sources identify as the actual true bottleneck.
The data.
Yes. Let's say it's 2026. Part 108 is live. You have drones flying hundreds of miles of corridor every single day. Congratulations, you have solved the flight problem, but you've created a massive new nightmare.
Terabytes and terabytes of raw data flooding your servers every afternoon. This is where programs succeed or fail. Gathering the data safely is only 50% of the job. If a drone comes back with 20,000 high-resolution images of a solar farm and they just sit in a folder on a hard drive,
That data is completely useless.
it doesn't fix a broken panel. Raw data requires processing.
The sources focus heavily on photogrammetry and AI anomaly detection. Can you explain how that actually works in practice? Because it sounds like buzzwords, but it's really the core of the operation.
Sure. So photogrammetry is the process of taking thousands of overlapping 2D photos and using software to identify common tie points between them.
Okay.
The software stitches those photos together and stretches a 3D mesh over them, creating a perfect, navigable digital twin of a substation or a tower.
Oh, that's really cool.
Right. And once you have that digital twin, the AI anomaly detection comes in. The AI compares the 3D model from today against the model from 6 months ago.
To see what changed.
Exactly. It isn't just looking for obvious breaks. It's analyzing at the pixel level to flag a 2 mm sag in a transmission wire or a slight discoloration on a transformer housing.
And then what?
It highlights the issue and directly integrates it into the utility's asset management software, automatically generating a work order for an engineer.
That is seamless. But, we cannot ignore the security implications of capturing that level of detail.
It's a huge concern.
Because utilities operate under NERC CIP, that's Critical Infrastructure Protection Standards. They are legally mandated to protect the grid from physical and cyber threats.
Exactly. When you are using LiDAR and thermal imaging to create millimeter-accurate 3D digital twins of critical energy choke points, that data is incredibly sensitive.
Yeah, I'd imagine.
If a hostile state actor gains access to a utility's cloud storage, they don't just see pictures of power lines, they see the thermal vulnerabilities of every transformer in the region.
Oh, wow.
So the storage protocols, the encryption, and how third-party software vendors handle that data, those are massive compliance liabilities.
Which really highlights the fatal flaw in how some people approach this industry. So what does this all mean? If I go online, take a 2-week multiple choice course, and pass my FAA Part 107 exam, why shouldn't a major utility company trust me to go inspect their highly classified substation?
Well, this raises an important question because a Part 107 certificate just means you know how to read an airspace map and not fly into an airplane. It does not make you capable of managing enterprise utility workflows. The most expensive LiDAR drone in the world produces absolutely terrible data in the hands of someone who doesn't understand NERC CIP compliance.
Or how to properly bracket thermal images so the AI can actually read them.
Exactly.
This is a huge point emphasized by Red Raven UAS, and their entire philosophy rejects the idea of just buying drones and figuring it out later. They emphasize a program-first approach.
Which is critical. A program-first approach means you don't build your operations based on a flashy demo from a drone salesperson.
Right.
You standardize your standard operating procedures around your specific utility assets. If you want the AI to detect a millimeter of wire sag, the drone has to fly the exact same automated flight path at the exact same camera angle every single month.
And that requires whole team integration. The asset managers who analyze the data, the maintenance engineers who fix the towers.
They all need a baseline of UAS literacy so they know exactly how to task the pilots and what to expect from the deliverable.
It reframes the entire endeavor. You aren't running an aviation program. You're running a highly secure data collection program that just happens to use flying robots as the delivery mechanism.
That's a great way to put it. And it raises an important question for any organization looking at this mountain of complexity. How do you eat the elephant?
Right. How do you even start?
The industry consensus is that you have to phase it. You do not buy advanced LiDAR platforms and fixed-wing corridor mappers on day one.
You start small.
You start with phase one. Pick your highest value, lowest risk use case, maybe basic visual inspections of distribution lines.
Master the data workflow. Prove the ROI to the executives, secure the data pipeline.
Exactly. Once you have that foundation, you expand to phase two, integrate thermal or LiDAR, and build your operations toward that 2026 BVLOS scale.
It really is a profound evolution. I mean, we are watching one of the oldest, most foundational industries in the world actively trade their helicopters, their climbing harnesses, and a massive amount of human risk.
For institutional knowledge, automated AI data pipelines, and thermal imaging.
Yeah, they're completely rewriting the manual on how we keep the lights on.
And that transition is critical because, as we established at the top, the grid is aging and the margin for failure is practically zero.
Yeah.
But before we wrap up, there's one final thought that builds on that NERC CIP data security issue we touched on. Something for you, the listener, to mull over the next time you drive past a substation.
Let's hear it.
If utility companies are utilizing automated drones to map every single inch of our critical infrastructure from the sky, capturing millimeter-accurate structural details and thermal vulnerabilities of every choke point on the grid, what happens when that data is aggregated? As we successfully solve the physical reliability of the grid using these incredible aerial tools, are we inadvertently creating the ultimate perfect blueprint for a cybersecurity nightmare?
Wow. That is an incredibly sobering place to leave it.
Thanks for listening to the Red Raven UAS podcast. Visit redravenuas.com for consulting, training, and FAA Part 107 certification, and check out the current special pricing on our Part 107 course.